the screen and we'll do some work, do out some proof arguments on paper for these as well. So this is looking at divisibility, chapter 2. So number theory, a large part of it, of course, is concerned with the prime numbers and investigating properties of the prime numbers. And of course, everyone knows the definition of a prime number is an integer which has no factors other than itself and 1. Okay. Positive integer which has no factors other than itself, no positive factors other than itself and 1. So obviously that definition concerns the multiplication properties of the integers. So that's something that we're going to begin the study of here, looking at divisibility. Now, of course, on one level, we're all extremely familiar with this idea of one integer being cleanly or evenly divisible by another one. It's something you would have, the idea of which you would have met in primary school. You would have investigated numbers, and you would have, you would have been learning things about numbers like 6 is divisible by 2, or 6 is divisible by 3, but 6 is not divisible by 4. You can't divide 4 into 6 even. You can't split 6 sweets up into 4 separate piles of sweets, or equal piles of sweets, without subdividing the units. Okay. So there's a very, on one level, this is an extremely early number concept which you've been living with for a long time. So why are we bothering with it? Well, we want to set up a very clear formal mathematical definition of it, of this concept of divisibility in the integers, and also, rather than just learning to recognize patterns with it, but actually going a much step further, and this is where you kind of step into rigorous university level mathematics, where we're going to prove facts about it across the whole integers. Okay, rather than just looking at instances of the properties that it has, or learning to recognize the properties that it has, we're going to actually prove the properties. Okay, by making use of the definition. So there's a whole bunch. We're going to look at the definition now, and in Theorem 2.1, there's a whole bunch, 7 separate numbered properties of divisibility, and we're going to want to prove each one. So we'll be investigating divisibility like this, but also when we're proving them, I want to emphasize, these are nice beginning proofs to look at because they're fairly small. You can contain them all on one page, really, but they're also complicated enough to point out the important steps you go through when proving something, or steps you go through when you're discovering a proof or setting up a proof, and how to write it down properly. Okay, so let's look at the definition. So we have this idea of divisibility. We say that one integer is divisible, or one integer divides another one. So B divides A. That's what we say. And what's the definition of that? So when we say something like this, that B divides A, we introduce this new term divides, and then it's followed by if and only if. So then the statement that follows the if and only if is the exact is what we mean by the new term we're introducing. So we say that B divides A if and only if there exists another integer C, such that you can write A as B multiplied by C. Okay? So don't get too thrown off by this. It is just, the familiar fact about numbers you're familiar with from primary school. So you could say, let's look at an example of it. 2 divides 6. So B equals 2 and A equals 6. 2 divides 6. Why does 2 divide 6? Because there exists another integer, namely 3. C would be 3 here. And you can write your original 6 as 2 times that other integer. 6 is 2 times 3. Okay. And the reason 10 does not divide, so the reason 3 does not divide 10, say, if you have B equals 3 and A equals 10, well, the reason it doesn't divide it is because there is no other integer C which can fill in the gap here. You cannot write 10 equals 3 times another integer. Okay. You can certainly write 10 equals 3 times another number. That number is 10 divided by 3, 10/3, but the point is that's not an integer. So it is not possible to factorize 10 over the integers where one of the factors is 3. Okay. We'll also use the term factors or divisors to refer to B and C here. Any B and C you can put down there. Those are factors of A or divisors of A. And similarly, we can call A a multiple of B, a multiple of C. And the notation that we use, so we don't always write down the words B divides A or A is divisible by B. The notation we have is B divides A. So straight line, one set vertical straight line, and B on the left and A on the right. And it's read in English, when you're reading this, you read it as B divides A. Okay? It's just a compact one symbol notation. And similarly, if you can stick a line through it, just like you have equals and not equals, the same way you stick a line through equals, we can say B does not divide A. So it would be true to say, for instance, that 3 does not divide 10. 3 does not divide 10. And it is true to say that 2 divides 10. So we can write down 2 straight out. Of course, instantly now here is a stumbling block or a potential to write your mathematics incorrectly and to read the expressions incorrectly, because is this saying that A divides B or B divides A? So there's a definite ordering here. It isn't like equal sign where it doesn't matter what order you take the two things. If one thing is the same as another, it doesn't matter which one goes on the left and which one goes on the right. But here it is crucial that the thing on the left is the one doing the dividing, and the thing on the right is the thing being divided. So B divides A. Some examples mentioned there. We've already talked about those. Any questions about the definition? Okay. As you say, it's certainly nobody can claim this is a new idea for them. You've been acquainted with this kind of idea since going through primary school. Of course, some more fancy-sounding description you might make of it, we can refer to it as a two-place predicate. You met predicates in logic last year. A predicate is like a formula for a logical statement, like a logical statement that depends on variables. If you supply values to the variables, you get a logical statement, something which is true or false. So we call it a two-place predicate. There's two variables. The thing on the left is the divide sign, and the thing on the right. Okay. So what we want to do now is look at properties, or kind of discover and observe properties that the divisibility relation has. We're going to look at theorem 2.1, all 7 parts of it, and we're going to prove each part. And of course, the main ingredient, well, what are the ingredients of the proofs going to be? Well, we'll use any fact about the integers that we know of. And those will be just the normal algebraic facts about the integers, which are summarized in an axiomatic way on pages 1 and 2. But I mean, these facts are so familiar, I won't be laboriously referring back to which numbered axiom it is. So we'll just use normal algebraic manipulation of the integers. But then the second key thing we're going to use all the time is this definition up here. These are statements about divisibility. And here, this existent statement here, the existent integer c, such that a is equal to b times c, that's the definition of divisibility. So we'll be going back and forwards from the definition many times here when we're proving this. Let's just have a quick read through them, and then I'll switch to the pen and paper. And we have some technical terms associated. So first of all, the divisibility relation is reflexive, meaning that every integer divides itself. So a divides a for every a. Secondly, it's transitive. So transitive in this context means if you've got two divisibility facts, if a divides b and further b divides c, then the divisibility kind of travels through b onto c. So you then say that a divides c. The first thing divides the middle thing, and the middle thing divides the third thing, then the first thing also divides the third thing. So divisibility kind of travels through intermediates. That kind of idea is what we call transitivity.
So we have an example of that.
Yeah, so, well, an example, 2 divides 4, yeah? 4 divides 12, and also 2 divides 12. The first thing divides the last thing, yeah? So if you can factorize a large number C, and one of the factors is B, and that factor B you can factorize in turn and have A as one of its factors, then that means that you can also factorize the first number C so that A is one of the factors. So if you supply values to yourself, if you come up with an example of an A and B, which is divisible like this, and another number C, which B also divides, you will always find that the first number A divides the third number C. But the point here is that rather than just look at loads of examples, okay, so for sure we want to look at examples of it and understand it, but we want to go one step further. We want to actually prove it, prove that it must be the case. Okay, 2 divides 4 and 4 divides 12 is an easy to understand example, small numbers, but how can we be sure that this will always be true for gigantic numbers as well? So what we want to show is that it flows straight from the definition. So if you accept the definition, you have to accept this fact. Third thing is divisibility of linear combinations. So if we have, so these are the assumptions here, if A divides B and A divides another number C, then the conclusion is if you take any linear combination of B and C, any integer coefficients n and m, and look at the linear combination nb plus mc, then A will also divide that. I'll illustrate these with examples before we prove each one as well. 4 and 5 are short and snappy. First thing says 1 divides everything. Everything's divisible by 1. And everything's divisible by 1, and also everything divides 0. So 1 can divide anything, and 0 is divisible by everything. Which sometimes trips people up. How 0 behaves, sometimes people flip it around in their minds, I think. 0 also has this interesting property that the only thing that 0 divides is itself. Okay? So if you think of this statement, 0 divides A, what candidates or what things can take the place of A and keep the statement true? Well, there's only one thing, namely 0 itself. And lastly, as long as the number C is non-zero, then these two statements, A divides B and AC dividing BC, they're equivalent. You can pass from one to the other, or vice versa. Or if you like to think of it, if the factor C is in both places here, you can cancel it from both sides and reduce the divisibility statement to one like this. But we can only do that when C is non-zero. Okay, let's jump in and try and construct the proofs for each of these, and we'll look at quick examples if appropriate. So this is theorem 2.1. I'll experiment with actually filming the screen, but I don't think I think because of the light levels and stuff, it doesn't actually come up. So there's probably no. Tell you what, it's not worth the hassle. If I want to do that, I think I'm going to have to get a better laptop or a better camera. Okay, so the first property is Everything divides itself. Be flexible. So we want to take any integer a, and we want to make the conclusion that a divides a. That's what we're trying to prove. So leave a bit of a gap here. This is the conclusion we're trying to prove. So how do we prove it? Well, you see, if we want to make a conclusion about divisibility, we have to satisfy the definition of divisibility. And when you look at the definition, just at the top of the page in the notes, the definition says you can only say that a divides a if you can complete this equation with an integer. If you can find an integer that goes in here that allows you to say a is equal to this integer times a. So can you find one that goes in? Yeah. Yeah? What is it? 1. And it's always 1. Although if a is 0, it doesn't have to be 1. It could be anything. But yeah, 1 is the obvious. 1 is the answer. Whatever a is, as long as you stick 1 in there, this equation is going to be true. Therefore, you're going to satisfy the definition of divisibility. So you can conclude that a does indeed divide a. So we're just observe that. I mean, that's really all we need for the proof. Observe that you can write a as 1 times a. So you've got a on the left, and a is one of the factors on the right. Therefore, this a divides that a. Okay. So this a here, the a on the right, pops up here on the left. This a on the left is the a appearing there, if you like. Do we need to say anything more about that? Everything divides itself. Okay, transitivity. E.g., so that example I gave before was 2 divides 4 and 4 divides 12, and so 2 divides 12. Example I used. Well, we want to show that this is always the case. If you've got 2 divisibility statements here, where these 2 numbers are the same, the one being divided in the first one and the one doing the dividing in the second one, if those 2 numbers are the same, then it has to be that this one divides the last. Okay. Observe it's true here for these examples of these small numbers, but can we prove it's true? Now you have to look at the form of the statement you're trying to prove, and you notice it's an if-then statement. If A divides B and B divides C, then A divides C. Well, in order to prove such statements directly, of course, you must make the assumptions that are in the if part. So whatever's between the if and the then, you have to make those assumptions, okay? Because those are the conditions that we want to talk about. So you have to make the assumption that they're true. So we assume that A divides B and B divides C for some integers A, B, and C. Now, what we're trying to prove is that from these assumptions, we can make the conclusion that A divides C. So what we want to do is somewhere after a suitable gap, leave a middle-ish gap there, we want to make the conclusion that A divides C. 2 divides the 12, if you like. What we'd like to do is work backwards, or what we have to do is join the 2. We have to join these assumptions here to this conclusion. Remember, the definition is going to be a key tool all the time. What we want to do is unravel the conclusion using the definition of divisibility and unravel the assumptions as well. Okay. So how is it that you can conclude that A divides C The only way you can do that is if you complete this equation, C equals A times something. Yeah, and the thing that has to go in this gap has to be an integer. Yeah, is it B? Is it B?
Yeah.
Well, it certainly doesn't have to be, because in this example here, the thing that goes in the gap is 6, whereas the B is a 4, so that wouldn't be right. So it involves B, certainly. So you're thinking along the right lines. So the point is we have to get an integer in there. But let's unravel the assumptions as well. Remember, this straight line has a meaning. Has a meaning in terms of more fundamental facts about the integers. So A divides B. So this is unraveling these assumptions, i.e. we can say that there exists an integer, we'll call it A prime, such that B is equal to A prime times A. Why is that true? That's true because A divides B. So there is some other integer A prime. I could have called it something else, but I'll call it A prime because it's something associated to A. So B is equal to A prime times A. The point is A prime is an integer. And also, there exists a B prime such that C is B prime times B. These two things come from the definition of divisibility and the assumptions. Now this is where we're trying to get to. We're trying to get to some equation, C equals something times A, and start to see where they're going to come from. Because here we've got an equation with C in it on the left-hand side, and here we've got an equation with A in it on the right-hand side. We just mush the two together somehow. We should get it. So C is B prime times B. That's just one of the, I'm just repeating myself really, just repeating that. But we just want to replace this B with this expression here, which I'll just kind of do now. So this is going to be B prime times B prime times A prime. No, sorry. Yeah, B prime times A prime. So I'll B prime, and I replace the B with the A prime A. So really, we're just reorganizing the brackets. So that's a proof of that property. If A divides B and B divides C, so we make those assumptions, use facts about the integers, use the definition, and we end up with the conclusion that A divides C. It may be worth pointing out, I mean, what's the fact about integer multiplication we're using here? What do we call this fact that set me from this line down to this line? I was rearranging the brackets. Is the technical term we give to that?
Associativity.
Associativity, exactly. This is the associativity of multiplication of integers. Here I've written B prime multiplied by the integer A prime A, and here I'm referring to B prime times A prime, and then the result of that multiplied by the integer A. So that's switching up the brackets is associativity. So that's good. Justification to put in as well. Associativity of integer multiplication. So divisibility is transitive, we could say. It travels through intermediates, if you like. A divides B, B divides C, then A indeed will divide C. And it will travel through any number of intermediates. If you just kind of iterate this result, apply this result a few times, you have any kind of chain of divisibility statements all the time going from linking together like this, then the first thing will divide the last thing. Okay. Okay, any questions about that or queries about any of the arguments there? Notice also the way that ended up on the page. I made the assumptions. Well, that's just something I got straight from the question. The question told me to. It was an if-then statement, so I assumed everything after the if. I put the conclusion down straight away. That comes from the question. Then I unraveled both of them using the definition. So I was just following procedure, if you like. Then to join them together, then that was the creative bit in the middle. You have to think, look at what you've got, try and bridge the gap, if you like. So very often with lots of the problems we encounter in number theory like this, and the questions you're asked, coursework and exam, lots of them, that's a good approach to take. Be very clear on what you're starting with, be very clear on what the conclusion is, employ the definitions, any of the relevant definitions all over the place, make use of those, and then try and finally bridge the gap from the conditions of the problem to the conclusion you're trying to get to. Okay. On to the next one, property 3. Property 3 comes up a lot. We constantly refer back to it. This is divisibility of linear combinations. Again, look at it. It's an if-then statement. If A divides B and A divides something else, C, then A will divide any linear combination of B and C. So we assume that A divides B and A divides C for some integers B, A, B, and C. Okay, so that's, I've assumed, made the assumption. Now the conclusion I want to reach, you see, it says for all coefficients n and m. So for any choice of coefficients n and m, I want to reach the conclusion that A divides nb plus mc. So n and m have to be very, very general. There'll be no conditions on them or no restrictions on them. So I should just say let n and m be any two integers. Okay, now we can do this trick of writing down the conclusion. So I've introduced the A, B, and C. I've introduced my potentially any pair of coefficients. So somewhere down here, I can put the conclusion we're trying to get to. The structure looks very similar to the last problem, yeah? We got our assumptions quoted in terms of the divisibility relation, and the conclusion is quoted in terms of that as well. So we should unravel them both using the definition back to their meanings in terms of products of integers. Then we can use substitution or other algebraic properties of the integers to link us from the assumptions down to the conclusion. So how is it that you can make a conclusion like this? You can only make a conclusion like this if you satisfy the definition for the divisibility symbol. That is, you have to be able to write nb plus mc something times A. So our task is to fill this gap, to fill it with an integer, to prove that there must be some integer which fills the gap. So to unravel the assumptions, so from the assumptions and the definition of divisibility, we get a couple of things. Again, the existence of a beta and gamma, so there's two integers beta and gamma such that there's two things we know. B is beta times A, and C is gamma times A. So that's unraveling both of the divisibility statements at the top. Okay. So here we see A is a factor of B, and beta is the other complementary factor, and A is also a factor of C, so the second one is saying, and I've named gamma as the complementary factor. Well, this looks doable now, because the conclusion I'm trying to get to is an equation. I want to fill the gap in an equation about NB plus NC. And I've got two equations at my disposal, one for B and one for C. So, I mean, I just want to manufacture this left-hand side using these two equations. So I can say then NB plus MC well, it's just this. Okay, just substitute the two equations in there. NB plus MC is going to be N times B plus M times C, and just use this other representation of them now. If we want to be very careful about it, it's again associativity. I want to move the brackets over. It's associativity and a bit of factorization. I want to write this as N beta times A plus N gamma times A. We've got two multiples of A, so we can factorize that whole thing. N beta plus N gamma times A. Any other thing you might ask yourself, is this an integer? Is this thing in the brackets an integer?
Yes.
Yeah. Why? In one word, why? Why is this an integer?
Because all of them are integers.
Because it's got four ingredients, integers. We multiply them, we add them, that stays within the integers. So if n, beta, m, and gamma are integers, then so must this thing. Yeah. So that's the thing that fills the gap. So linear combinations, if you like, preserve the divisibility of the components of the linear combination. Any questions about that, or any queries? Anything you'd like me to clarify on it, or? Okay, let's get to the end. Before the end. So what you should be extracting out of this? We're confirming or learning or confirming properties of divisibility, but also learning at the same time strategies for constructing proofs. Okay. So this idea: be very clear about the beginning assumptions, be very clear about the end conclusion, and so oftentimes you can try and work together from both ends to try and join them in the middle. So property 4, 1 divides everything. I mean, this is really a one-liner. The only way you can say that 1 divides A is if you can write A as something times 1. And what's the something? A, of course. A is A times 1. I mean, that's all that there is to say about it, really. Yeah. So 1 divides everything. Everything is divisible by 1. You've got a collection of A sweets. Can you divide them into one group of sweets? Yeah, you can. They're already divided. You know, it's just whatever group it is. So it's not really saying that much. Everything divides 0. So here's the thing, A. I want to conclude that A divides 0. So in order to make that conclusion, no, sorry, see, I did it wrong. I have to be able to write out this kind of statement. I have to show that A is a factor of 0. Is it? What's the other complementary factor? 0. So yeah, you can factorize 0. You can factorize 0 and you can produce any other number as a factor. So if you've got no sweets, can you evenly divide no sweets into 100 different groups and give 100 different children the same number of sweets? Yeah, you just give them all no sweets. Tough luck, kids, but that's the way it is. So 0 is divisible by everything. Now, I like the way you got to remember the ordering, the meaning of the left thing and the meaning of the right thing in the divisibility symbol itself. Also, you got to not to misremember the properties of 0. Some people they misremember it or they misquote it and they say 0 divides everything. That's not true. 1 divides everything, but 0 can divide very few things. And property 6 says that 0 divides only itself. Sorry, what? Yeah, I keep writing it. So we let A be an integer, and we want to assume that 0 divides this integer, and we want to reach the conclusion that A is 0. So the only thing you can put in the right-hand side is 0. Again, it's just a one-liner, really, I think. It's just unraveling the definition. What's the definition of this symbol? That 0 divides A. If you look back to the top of the page, sorry, yeah?
What is 0 divided by 0?
What is 0 divided by 0? So if you have 0 things, and you split it into 0 different groups, how many things is in each group? Well,
if you type it on a calculator, it doesn't like it.
Yeah, it doesn't like it, yeah. Well, that's not the fundamental answer, I guess. Or maybe it is. But can you divide something into 0 groups?
So I was thinking of looking at it as a statement.
It doesn't make any sense, yeah. So, zero horizontal line 0 doesn't have there isn't any reasonable definition you can give to that. Some people would say if you have 5 divided by 0, some people would say that's infinity. Well, some people would say it's undefined as well. I mean, it is perhaps a reasonable thing to say 5 divided by 0 is infinity, because if you take the limit of 5 divided by something, you take the limit of that as the something approaches 0, then that expression 5 over something will be divergent. But for us, here in this integer world, studying number theory, 0 divided by 0, it's not a valid instruction. It's
But isn't this claiming that it's an integer?
Well, yeah. No. No, it's saying if so 0 divides A, that can only be true if A is equal to something times 0, where the something is an element of the integers. So the question is, when is this statement true?
For all integers?
Yeah, for all integers.
For all integers. Well, if A is 0, you can stick any integer in there. Yeah. So if A is 0, you can certainly say 0 divides 0, because you can stick anything in there. Stick 2 in there. 0 is equal to 2 times 0. And is it true in any other situation apart from this? No, there can't be anything other than 0 on the left-hand side. So if there was, let's pretend that 2 is here. So 2 is equal to something times 0. Well, that can't be true. Because every integer you try and put in here, it always spits out 0 here. And that's really all this is. It's just the observation that this kind of statement can only ever be true. That's why it's implying that A must be 0. So 0, are there any numbers that 0 divides? Yeah, just 0. Now, your question of 0 over 0, it's slightly different. There you're talking about, what is the fraction 0 divided by 0? That's a slightly different thing to say to us saying in the integer sense, yeah, is there any integer that's divisible by 0? It's, I don't think there's any great mystery or a great kind of weird fact about the universe hidden here. I think it's just a matter of notation and definitions of words on that. Yeah, go on.
So here we're proving that 0 can be divided by 0, not what 0 divided by 0 is. Or are we saying 0 divided by 0 is 0?
Basically,
I don't understand.
I think what we're proving is the only way of completing this equation. The only situations where you can complete this equation is where you've got 0 on the left-hand side. And I wouldn't make any claims stronger than that.
So does it mean the definition, the number divided by itself is 1, is not 2?
Well, well, it's true except for the case 0.
But 0 is a number.
Yeah, 0 is a number, yeah. So any non-zero number divided by itself is 1. If you like, you can consider this as like an edge case of definition. Things like divisibility and so on. Yeah, you've got a good intuitive notion of them from your mathematical experience. This is just a case on the very edge of the definition. You just have to be a little bit careful, but it's not like we're discovering some great thing about the universe here. It's just a matter of what the symbol means. And for us, remember, this symbol, divisibility, what it means is when you can fill the gap with an integer. So in that purposes, the only way you can fill the gap there is when you've got 0 here. And then you can fill it with whatever integer you like. Just in time for the last one, I think. So here we have to assume C is non-zero. And what we're trying to prove is that A divides B is equivalent to AC divides BC. So all we have to do is just note that that itself is equivalent to the same statement using the definition. So B equals some alpha times A and is that equivalent to sorry, I think I'm presenting that kind of bad. So I'll start again with that. Assume C is non-zero, and let's think of A dividing B. Well, that's true if and only if B is equal to some alpha times A. Yeah. And that we can say that this is true if and only if B is some alpha times C. Sorry, if BC is some alpha C times A. So you're just multiplying both sides by C. And is this, so I've claimed it's equivalent to the previous thing. That's where you need this important thing that C is non-zero. Because I can get from the top to here by multiplying both sides by C. To go the other way, get the logical implication the other way, of course, you need to divide by C. And that only makes sense, kind of linked to our previous discussion, only makes sense if C is non-zero. So this way is multiply by C. And to get the backwards equivalence, you're dividing by C. But there, of course, you need the assumption that C is non-zero, which we haven't even made. BC equal to something times A, that's equivalent to saying that, well, if you bracket it like this, that AC divides BC. So the two are equivalent. So you can cancel from both parts of the divisibility statement. You can cancel something non-zero, a non-zero factor, from both parts of the divisibility statement.